Welcome. This is the ECEN-160 Final Project Microprocessor, as designed by Samuel Kuntz. Here we have an 8-bit counter. This counter increments by 1 each clock cycle. The signal is fed into this PROM. This PROM contains the program that we wish to run on this processor. As the counter increments, the PROM will move to the next instruction in the program. This PROM outputs 8 bits representing the program. Bits 0 through 3 from the PROM consist of data to be written to the register file, which will go this way. Bits 4 through 7 pass down to the instruction decoder. The decoder takes the instructions from the PROM and sends the enabling signals to the various components of the processor, allowing the processor to actually perform the functions as desired in the program. Here we have a MUX, which allows us to select the source of the data that will be stored in our register file. We can write to the register file from either the program that is output from the PROM, or we can write from the accumulator built into the arithmetic logic unit. Next we have the register file. This register file consists of a demultiplexer that determines which register the data is stored in, and 2 4-bit registers. Each of these 4-bit registers consists of 4 1-bit registers wired together to create our 4-bit register. And each of these 1-bit registers consists of a demultiplexer and a deflop wired together like this. Next up, we have the arithmetic logic unit with the accumulator. The arithmetic logic unit consists of an addition subcircuit, bitwise OR, and an exclusive OR subcircuits, a demultiplexer, and another 4-bit register, the same as we have used before. Here's an example of the bitwise OR subcircuit. The bitwise AND and bitwise XOR subcircuits are very similar in nature. Here's the addition subcircuit. We have 4 1-bit adders put together, as well as the circuitry that allows us to do a 2's complement to allow us to subtract using the hardware. Here is the 1-bit adder. And last but not least, we have a display for our microprocessor. Now that we've gone over the entire microprocessor, let's see how well this works. So the first part that it's doing is displaying the letters. To display the letters, the program first copies the first 4 bits of the ASCII code to one register, and then copies the second 4 bits to the second register. Then the program issues the command to write what is in the registers to the screen. Now to add, each number will be copied to a register, and the program issues the instructions to add register 1 and 0. This output is stored in the ALU's accumulator and then sent back out to the screen. To multiply, the 2 values are copied to the register. The ALU adds them and stores the value in this accumulator. The accumulator is then copied to register 0, and the ALU adds the new values. This process is continued over and over until the multiplication is complete and the output is performed like the addition. To subtract using the software, we need to create a 2's complement of the subtrahend. This is done by performing a bitwise XOR, exclusive OR, with the subtrahend and the largest number that we can store, in this case 1111, and then adding 1. This 2's complemented data is fed back into the original register, and then both registers are added again. The output is displayed just as the addition we did earlier. Now to subtract using the hardware, we put the minuend into register 0, put the subtrahend in register 1, and send the command to subtract. This activates the subtraction hardware in the ALU, which performs the 2's complement in hardware. The output is displayed just like the addition we did earlier. Now that we've run out of program, it will continually loop. So our program is now complete. I hope you enjoyed this demonstration.